This lesson is on Raleigh's theorem and the mean value theorem. These are two very similar theorems. Raleigh's theorem is actually used to prove the mean value theorem. And they refer to, or they both have very similar initial conditions that they work with. So we're going to start with what's called Raleigh's theorem, or some people call it Rolle's theorem. I don't know the guy, so I don't know what it's really called. I don't care what you call it. But the initial conditions of this are what's important. So f, this function, is continuous function on a closed interval a to b. So it gets from this point to this point, with the endpoints included because it's a closed interval, as a continuous function. And it's differentiable on the open interval a to b, meaning you can find its derivative, or its derivative is defined everywhere between those 2 points. The last part of Raleigh's theorem says that f of a is equal to f of b, meaning the value of the function at a is equal to the value of the function at b. They're the same height. Raleigh's theorem says that if you have a function where the endpoints of the interval are the same height, the same y value, and the function is continuous and differentiable between those two endpoints, that the slope of that function, that the derivative of that function, must equal 0 at least one point between a and b. So somewhere between those 2 points, the derivative of the function must equal 0. What that basically says is if you have a function, you start here, you end up here, and you travel in such a way that's continuous and differentiable the whole way, you got to turn around. The function has to turn around. So the function could go up and come back down, could go down and come back up. It could also do that more than once. It's like if you think of a trig function, a wave function, you could turn around numerous times. The main idea is that it has to happen at least once. So f prime of c must equal 0 for some c where a is less than c is less than b. Meaning at some c in between a and b, some value here, the derivative is 0. So if I drew the function so that it's continuous and differentiable, meaning no sharp turns or no breaks in the function, somewhere around here, this would be my value of c. Has to happen at least once. The mean value theorem expands this idea. Has the same initial condition that the function is continuous on a closed interval and differentiable on the open interval. But it crosses out that last part. No longer do the endpoints have to be the same height. You could start at one endpoint, finish at a different height. If you think about, I'm going to give you an example, a real-world example that you might be able to understand that really gets the idea of the mean value theorem across. If you think about something like if you're driving a car and you leave from here and you travel somewhere 300 miles away. So you take a 300-mile trip and you reach there in 6 hours. Well, if you think about that, you are averaging 50 miles an hour. You travel 300 miles in 6 hours, so your average rate was 50 miles per hour. Now, more than likely, you weren't going 50 miles an hour the whole way. You were going, you started off slow, major highways, you were probably going 60, 70, in through towns and stuff, or through lights or smaller highways, you were going under 50. But your average speed was 50 miles an hour. But the mean value theorem says if your average speed is something, whatever that value is, then you have to hit that value at least once. So if you use that trip, that car driving analogy, although you weren't traveling 50 miles an hour the whole way, there was at least one time during that trip where you were going exactly 50 miles an hour. More than likely in that analogy, at least 2 times. Maybe you went above 50 and then you dropped below 50 at some point, so there were 2 different times when you were going 50. But the mean value theorem for a curve says that if the function is continuous and differentiable in the interval, f prime of c, the derivative at some point c between a and b, is equal to f of b minus f of a over b minus a. Here's the formal statement from the mean value theorem. What this says is that the instantaneous speed, the derivative of the function, the slope of the tangent line, is equal to the average speed from the endpoints, from one endpoint to the other, which is the slope of the secant line. So the slope of the tangent line is equal to the slope of the secant line at least one point, meaning the tangent line is parallel to the secant line. So if you're traveling, or if you have this differentiable continuous function from a to b, the average speed of that, which is the slope of your secant line. So there's your secant line. And let's say I drew a function like that. Continuous and differentiable the whole way. What this mean value theorem says is that the slope of the tangent line has to be equal to the slope of the secant line at least one value. So what I'd be looking for was a tangent line that's parallel to the secant line. And it looks like somewhere in there. So there would be one value, and somewhere around there. So this particular function has 2 points, where the tangent line is the exact same slope as the secant line, where the instantaneous rate is the exact same as the average rate, where the tangent line and the secant line are parallel. The mean value theorem guarantees this happens at least once on that interval. Now we'll walk through one problem using the mean value theorem. Determine whether the mean value theorem can be applied, and if so, find all values of c guaranteed by the mean value theorem. So the first part says determine whether the mean value theorem can be applied. So we have to check, see if the function is continuous and differentiable on that interval. So the function is f of x equals x cubed. Well, x cubed is always continuous, always differentiable, so the mean value theorem can be applied. Now we have to find the value of c guaranteed by the mean value theorem. Remember that says slope of the tangent line equals slope of the secant line. So I need to find the slope of the secant line from 0 to 1. Well, the point at 0, 0, 0, f of 0 is 0, f of 1 is 1. 0 cubed, 1 cubed. So I want to find the slope of the secant line. I take difference of the y's, which is 1 minus 1, over difference of the x's. I'm sorry, 1 minus 0 over 1 minus 0. So you get 1 over 1. So the slope of your secant line of f of x equals x cubed from 0 to 1 is 1. The mean value theorem says that the slope of the tangent line has to equal 1 somewhere between 0 and 1. Well, the slope of the tangent line is found by using the derivative. So I take the derivative, which is 3x squared, set that equal to the slope of the secant line. 3x squared equals 1. Solve for x. Divide by 3, take the square root. So x is equal to square root of 1/3. So you have a positive square root of 1/3, negative square root of 1/3. If you simplify, you get radical 3 over 3. There's 2 values for which x, here, the slope of the graph equals 1, at positive radical 3 over 3, and negative radical 3 over 3. But the only answer for this problem is the one that's on the interval. So we're only looking at the positive value. Square root of 3 is about 1.7, so 1.7 over 3 is a little more than a half, which is in between 0 and 1. So at x equals radical 3 over 3, the tangent line to this graph would be parallel to the secant line between those 2 points, between those 2 endpoints.